It's my great pleasure to present our next speaker, who I work with on a regular basis. He's been teaching me the gentle art of how to troll rich. And so I'm getting better at it, but I still have a long ways to go. So without further ado, Stu Halloway.
Good morning, everybody. My name is Stuart Halloway. I'm going to be talking about ETL jobs in Clojure and Datomic. And this is something that, there's sort of big E enterprise ETL that has all kinds of ilities and buzzwords, but there's also sort of small E ETL, which is that all the time, as developers, we find ourselves in a situation where we have data in a box over here, and we need to move that data to a box over there, and along the way, filter, transform, correct errors, and so forth. And when I started working with Clojure, I was confident that Clojure was a fantastic language for doing this kind of work for a variety of reasons. And when we first built Datomic, we did a theoretically one-time ETL job to get the MusicBrainz dataset, which is in Postgres, and put it into Datomic as a sample dataset. And that has, multiple people have looked at that ETL job on and off over the years. And frankly, it's been years prior to a month ago since I thought about that ETL job. And we've never really talked about ETL into Datomic. I don't think there's been a conference talk that we've done about that or an article or anything like that. And I decided that it would be fun to revisit that in light of things that Clojure has picked up since we did the original job. So when we wrote that original ETL job, Clojure did not have spec. Clojure did not have transducers. Clojure did not have core async. For that matter, Datomic did not have nested entity maps and lookup refs. So there are all kinds of things that I wanted to go back and see how I would feel about this job, revisiting it in light of these new tools. So from a simple-minded perspective, extract, transform, load is just that. It's 3 steps, right? You've got a data source, you extract, you transform, you load, and you end up with data in some destination. But when you start to break it apart, you realize that that is a very facile assumption, and that there are probably a lot more steps. There might be more than one data source. There might be more than one destination. You might need to do integrity checks on the data coming in to make sure that it's not corrupted. You might want to clean up errors in the data. You might want to filter some data out or join in data from an alternate source. And so it quickly turns into potentially a wad of spaghetti, whereas it was originally just this sort of 3-step process. And I'm going to tell you right now that you can go and look at articles and books that break up these steps. If you read the first 30 Wikipedia hits on something, which I always do before I give a conference talk, because you don't want to be sort of surprised by some random craziness that people out in the world have said about things. But if you look at the first 30 Wikipedia hits, you'll see this job sliced up a million different ways. And I'm here to tell you that the exact steps don't really matter. And whatever you think the exact steps are, you're probably going to discover after you finish it that you need different steps, or that you need to add a step, or you need to fold together some steps for performance, or parallelize a step, or whatever. But how you do compose the steps matters a lot. And the right way to think about this is a functional pipeline, that you have a series of steps, each one of which is a functional transformation of data to data. So there's not a lot of sort of magic mutability or updates or other things in there. It really is just a pure function of data to data, followed by another pure function of data to data, followed by another pure function of data to data. And when you think about it this way, all kinds of nice things become possible that might not have been possible if you approached it a different way. So if you decide to go back and parallelize that, you're a good fraction of the way towards being able to do that. If you want to make intermediate steps durable, right, you've already described your transformations in those terms. If you need to checkpoint your job because something's going to go wrong, and it will, then having broken it into these steps gives you, straightforward places to do that, and also ability to get feedback. So you start the job and you realize that something didn't work, you get feedback, you adjust and recover, and don't have to go all the way back to the beginning. So there are several obvious advantages to using Clojure for this kind of work. The JVM is super powerful. The REPL is a fantastic interactive place to explore. We encourage a data-oriented approach to programming, and now we have Clojure spec. I'm not going to talk about all of these in detail because that's sort of Clojure 101 type stuff, but I do want to mention a couple of things. One of them is this sort of notion of data-oriented functional programming. I think that we can do a better job when we're evangelizing Clojure to people who are coming to the language of talking about exactly what this means and how it distinguishes Clojure from other approaches. In particular, the pair of words systemic generality. So Clojure encourages you to program with a small set of functions that can operate on a generic data structures. It doesn't just do that, though. It takes that systemic generality everywhere in your application stack. Right? It's not just about your program. It's also about configuration data, which could be in Eden or Transit. It's also about data on the wire. It's also about exceptions and errors when things go wrong, representing that as information. And so it's not just sort of a local phenomenon. It really is a systemic phenomenon in thinking about programming this way. And this is important because when people talk about Clojure, they tend to lump it in with scripting languages. They tend to say that over here, you have these statically typed languages, C# and Java and so forth. And over here, you have Ruby and Python. And, well, Clojure is dynamically typed, so it goes over here in the Ruby and Python bucket. And I think that that undersells Clojure, because I think that the more important distinction is that regardless of whether you're using statically or dynamically typed languages, most of these languages encourage what I'm going to call encapsulated specificity. Right? So regardless of whether you're in a language like Ruby or a language like Java, you walk up to a problem domain and you immediately start writing into code specific things. Right? I'm going to make a person class and an order class and an order line item class. And the static dynamic typing thing is a little bit of a distraction to that. Right? We're doing that regardless of what language we're in, unless you're in Clojure. And so I think this is a big point. It's a little bit ancillary to my talk today, but I want to get this out there so that when you're trying to explain Clojure to people and talking about what's going on, you don't have to accept just being dropped into a bucket with Ruby and Python, which is not the bucket that we want to be in, I think. Then you talk about spec. So spec is obviously new in Clojure 1.9, and it is designed to allow you to talk about specific things. I mean, I just said we're going to talk generally, right? We're going to take this approach of systemic generality, and now we can introduce specificity in a very Clojure-oriented way, right? We can say we're going to talk about specific things with data, and then we're going to leverage that data at times and places of our choosing. I've given several talks about this. The one that I gave last night for the Austin group is going to be up on video. There's one from Strange Loop. I won't go through all the details again, and in particular, I'm not going to talk about all the different points that are made on this comparison table between spec and static types and tests as a road to trying to understand if your program works. I just want to point out really the bottom row here, which is reach. Because doing an ETL job is all about reach. Right? It's by definition being in at least 3 places, right? Being in the source data, being in your program, and being in the destination data. So this is a place where spec really shines. And when I approached this MusicBrainz ETL job, I was approaching a brownfield thing, right? It was a thing that was written by some malicious Clojure developers, people like Bobby Calderwood, over the last several years, and it had, a lot of traps laid there for the unwary. And so I walk back to this program, and of course you see the classic Clojure code that was written 5 years ago. It's a bunch of functions that are manipulating stuff, and you look at a function and you go, I have no idea what keys this map is supposed to have. Right? And this is one of the motivating things that led people to doing things like Plumatic schema. It's also one of the motivating things that led to spec. And I had a hypothesis that I could use spec in a really dynamic way to rediscover a code base that I had forgotten. And that really turned out to be the case. And so what I ended up doing was describing the input side of the data as map specs. And so an artist in the system is required to have a global ID and a sort name and a name. And optionally, it also has a type and a gender and a country. And by doing this, I could then strap this spec on. I could run all the data through a conformer and say, am I right? Or, what did I not know about? I could also strap this on to functions that were processing the data, an instrument, and say, hey, stop me, pull me up short if I'm mistaken about the facts of the system. And the dynamic nature of this meant that I could bandage exactly enough to get my understanding up to the level where I could work in the system. Okay, which is a lot different from, say, flowing static types, where it's like, okay, I add this everywhere, right? You stick your finger in the wall, and then, now you have to do this, kind of everywhere in your system. I could do exactly as much as I wanted to. I also want to make one other point here. I was working with legacy data in the sense that the maps had unqualified keywords. And people are wondering why I and other people keep going on and on about qualified keywords. If my data had qualified keywords, then specs would have been able to pick up and validate things I didn't even notice. Right? So I have a bunch of keywords listed here in a comment that also happen to appear in artists sometimes. And let's imagine that I didn't know that when I wrote the map spec. Right? If I were using qualified keywords everywhere, then those things would be self-identifying. And when spec was validating, even though I didn't know about them, when I talked about it, spec would know about them and be able to validate. Now, I chose, for reasons of this talk, which I've written sort of between midnight and 2 a.m. over the last couple of weeks, I chose not to go back and make this data change, right? Which is another important point, right? That would have been additional leverage. If I had used namespace qualified keywords, I would have gotten more leverage here. But I decided, you know what? It's good enough. It's not the place I want to focus on, so I'm going to move on. I did write a little helper function called conform bang that is like conform, but throws an exception with data in it. And I end up writing this function in every spec project that I ever use, which means I now hereby submit it to the rich name rejection system. So Rich will mock that name for a while, and then either come up with a better name and include this somewhere, or come up with a way to think about this more generally and include it somewhere. So I'm looking forward to see what happens there. So that's kind of obvious advantages of using Clojure, having the ability to describe things as functions, being able to use spec, and come back to existing systems. There are some less obvious advantages, and I want to spend more time on these. And this is transducers, strong namespaces, reified transactions in Datomic, and universal schema in Datomic. And I'll start with transducers. And I have to admit that when transducers came out, I didn't use them a ton. I mean, I was involved in the development, but I'm working on this legacy code-based Datomic that was on an older version of code at some point, and I didn't want to go back and just change things willy-nilly, and so I didn't. But I thought, what would it be like to approach an existing thing that's not written with transducers and replace the pieces with transducers? And 3 things happened. The first thing was kind of obvious, right? Transducers, if you go and look at the single paragraph about them at the top of the page, it's going to tell you that they decouple transformation from input and output sources. And that's what they're about, right? So you describe algorithmic transformations without talking about inputs and outputs, and then you can sort of strap that on in the manner of your choosing later. That's obvious, and by itself, that sounds like a good fit for functional pipelines. But 2 things fell out that are maybe a little bit less evident. One, it made accidental complexity in the system more evident because it gave it fewer places to hide. So imagine a function that's doing a transformation that does a little bit of work with input, and a little bit of transformation, and a little bit of output, and some stupid stuff. Right? It's a function that's doing 4 things. And so when you're reading, especially when you didn't write it, right? You're reading it, you're trying to fix something else, right? The stupid stuff now represents 25% of the function, and it's easy to miss. Now imagine a world where you're using transducers, and the input and the output has been pulled out of that function. So now all you have in that function is transformation and stupid stuff. And you look at that function and you go, wow, the stupid stuff looks really stupid. I should get rid of that, and it becomes easier to see. The other thing that happens is when you start doing that is you discover commonality. And admittedly, this is commonality that would be present if you thought about it for 5 minutes anyway. But you know me, I'm like most developers, I just like to type, right? So I don't really want to think for 5 minutes before I start typing. So I'm just sort of banging along there. But with transducers, those common things become more visible. And so what happened when I went back to the ETL job was I ended up writing this case statement that said, you know what, I've got to convert 8 or 9 or 10 different kinds of entities, and I'm going to force myself to go through and describe every one of those entity conversions as a transduction. Right? None of those 10 entity conversions were described as transductions before because transducers didn't exist, and some of the transductions were entirely trivial. But once I wrote it this way, it became blindingly obvious that there was this helper function hiding in there called transform entity, whose logic was split out across a bunch of different places and didn't appear in some places where it could have appeared and had some ad hoc code. Now, could I have done this by thinking about it and lying on a hammock? Yes, I absolutely could have. But just by adopting the rule that I have to write this stuff as transducers, it was actually impossible to avoid noticing this opportunity for reuse that had not occurred through at least a half dozen revisions of this ETL job. And so I was able to discover this piece of fairly generic code and pull it out. The other thing that's going on with transducers right now is Clojure 1.9 gets halt when, which is also an easy thing to backport if you want to just grab it and pull it back and use it. And what this does is it's a transducer that stops the transduction when some predicate matches. And so the transducer I'm showing here is actually a transducer that transacts against the Datomic client API and then stops if there's a transaction that failed for some reason. And this is really cool. And when you're in the transduction business, you really don't want to be in the errors as exceptions business. You really want to be in the errors as information business. And so the idea of halt when now brings up, how are we going to represent errors as information? Well, the obvious thing to do, to some degree, because we're running on the JVM, is ask Java how they think about errors. And so when you go down that road, you end up looking at Java's exception hierarchy. And Java's exception hierarchy is problematic for this job because its dominant axis is checked versus unchecked exceptions, which is like a type theory exercise that is perhaps proven not to be that valuable. But because that's the dominant axis, it doesn't provide a categoric split to say, well, over in this branch of the exception hierarchy, these are the kinds of errors that mean your program is broken, and you should go fix it. And over in this branch of the exception hierarchy, these are the ones that mean the program you're talking to is broken, and you should tell them to go fix it. And this branch of errors over here represents the different kinds of things that are actually actionable when an exception happens. And if you've tried to write programs that run on the JVM, you've felt this problem. Right? You want to say, I want to take action. These are recoverable things that I can take action. These are things that I want to report to somebody, and these are things I want to report to somebody else. And you want to try to map that to exceptions, and it doesn't work. And then you look at things like, if you're doing JDBC, SQL exception. Right? Down underneath SQL exception, all those categories occur again, which means that if your thing might ever talk to SQL, you have to do that and branch again. So pretty quickly decided that I did not want to make the centerpiece of errors as information the Java exception model. So then, if Duke can't help, I went and said, OK, well, let's go and ask this guy who invented the internet how we want to do it. Well, how does the internet think about this problem? The internet thinks about this problem with these HTTP status codes. And where Java had a type system bias, these status codes are better. Like if you told me I had to use Java exceptions or I had to use HTTP status codes as my mechanism for talking about errors across the whole universe, I might actually choose HTTP status codes, even though I'm very rarely going to have a program that has a teapot or some of the various other things that are in the HTTP status code spec. But it still has a very place bias, right? All the 3 codes are about you should be talking to a different place. All the 4 codes are about it happened in your place. And all the 5 codes are about it happened over there. Well, that doesn't really make sense either, because my question is my input invalid? Well, if my input's invalid and the client decides it's invalid, that's a 4, and the server decides it's invalid, that's a 5. I mean, that doesn't really fit so well either. And I realized that as much as Duke or Al Gore, have been important figures in contributing to the history of software development, that I was going to really have to bring out the big guns. I was going to have to go back to, as we always do in Clojure, I was going to have to go back to the 1970s and dig up some ancient tome and find how we should solve this problem. And so I did. And what I discovered was that in secret, over several decades, Hall & Oates have carefully thought through this problem. And they have produced a set of songs that indicate the categoric things that you might want to do when you encounter an error in your program. Right? The resource could be unavailable, in which case you're out of touch. You could have been interrupted. It doesn't matter anymore. You could be incorrect. You'll never learn. It could be forbidden. I can't go for that. It Could be unsupported. In your imagination, I'll do that operation for you. Something could be not found. She's gone, baby. Conflict, give it up. This isn't going to work. You could have a fault, we're failing here. Or you could be busy, wait for me, come back and try again, and I'll be good. So this is now my favorite open source library that I've ever created. This open source library is exactly 11 lines long. There's these 9 lines in spec. There's a spec that says there's a named keyword that can refer to one of these, and then there's another spec that says there's a string message that can add detail on top of this. This is shipping with Datomic clients. It's open source. I will get a GitHub repo up with this, or maybe I'll just put it in a tweet. Another less obvious advantage is strong namespaces. And this is a real sleeper thing when you first approach Clojure, because you're used to namespaces. But namespaces in most programming languages correspond to stuff. Right? For a namespace to exist, there has to be stuff. There has to be a class. There has to be a package. There has to be a whatever. But Clojure's namespaces are really at the bottom. Right? Clojure's namespaces are properties of names. They're a property of symbols. They're a property of keywords. And they're connected to spec. And they are literally, a word that I hate for people to misuse, they are literally easy to use because they are literals. Right? They exist down in Eden, separate from anything else. And what this lets you do, and I didn't say this earlier talking about ETL jobs, is when you go back and think about all these different phases of the job, each one of these phases might have some knowledge of names that you want to spec. And you can put each one of those phases in a different namespace, and then that data can cohabitate. So maybe there's some job that's going from namespace 1 to namespace 2. You want to have both of those namespaces in play. You don't want to burn the good names. You don't want to have to reify anything. So this is a really big help. And a message that I would send to Clojure programmers in 2016, namespaces are good. Right? If you make a new thing, make a new namespace. Do not change the meaning of names in an existing namespace. Just stop doing that. Right? We do not have a namespace shortage. There are even more namespaces than there are UUIDs. Right? We are not short of namespaces. In fact, each one of you, under any internet domain of your choice, have more namespaces than there are UUIDs. And by the way, Microsoft wasn't wrong. It's perfectly OK to name something foo2. Right? If foo is really the best name for it and you make another one and you change the semantics, then foo2 is perfectly OK. Another less obvious advantage is reified transactions. And Tim Ewald gave a talk on reified transactions last year at the Datomic mini-conf before ClojureConf. I'd recommend that you watch that if you're interested in this. But the idea is that in Datomic, transactions are entities like any other entity in the system, and transactions are a durable record of operation. Right? Just as you have records about people, or in our case, songs and tracks and whatever, you have records about what you did to the system. And you can put your own attributes on these transactions. So when I put together the importer, I added an attribute called mbrains.initialimport/batchID. And that attribute is on every transaction now that puts data into the system. And this gives you a whole bunch of different things. One, it establishes provenance. Right? Anybody who comes back to this data later can say, where did this data come from? Oh, look, there's an attribute on the transactions. It says it's the mbrains initial import. I could put more attributes there, too. I could have URLs pointing back to the Postgres data that it came from, and so on and so forth. And that data will live with the actual mbrains data as long as it's there. This also provides a way of tracking progress. I can walk up to a system whose import state is unknown to me and issue a query for these batch IDs and say, hey, has the import happened? Did part of the import happen? That part of the import question means that I can make the import restartable. Right? When I screw it up, as I've done about 7,000 times now, right, I can go back and say, hey, what part of the import was done? And also, this supports, although does not by itself fully enable, this supports parallel and pipelined imports. Right? Now, it may be that there are other things about my data. There may be ordering dependencies in my data that say that you have to put Fred in the system before you put Ethel in the system, or the system's not going to be happy. Right? But at least at this level of the system, and in fact, if I don't know if there are ordering dependencies, I can find out. Right? I can just try to parallel and pipeline data in using this technique, and anything that fails, I can just try again. Oh, look, there was an ordering dependency. Fine, I'll do that data again. Another less obvious advantage is the universal relation or universal schema in Datomic. So if you have a relational database, every time you want to model anything, you make a new relation. Right? There's a relation for people. There's a relation for tracks. There's a relation for albums. There's a relation for this. Well, everything in Datomic is a single relation. It's about datoms. Right? Everything just distills down to these 5 tuples: entity, attribute, value, transaction, and operation. And the obligatory Jane likes pizza example, right? So you have a datum that says some entity Jane has some property likes whose value is whatever as of some point in time, and are we adding this or removing this from the system? In this case, we've added broccoli and pizza and then removed pizza. And what does this have to do with ETL jobs? Well, a couple of things. When you use a universal schema, the logical schema, the thing that people talk about in the SQL world, has an almost one-to-one correspondence with your physical schema. Because you don't have to talk about things like join tables. How many tables are there in Datomic, really? 1. Right? There aren't any join tables, so you don't have to talk about that. Likewise, it automatically biases you towards being a database, storing information, not storing the answers to questions. This is in stark contrast to, for example, Cassandra or Mongo, where the best practice, because of the other properties of those systems, the best practice is you make a table per query you're going to ask. Oh, I might need to ask this question in the future. All right, make a table with all the information in it. You might need to ask that question in the future. Make another table with all the information in it. And so when you're using a system that has that bias, your ETL job has to anticipate what questions you're going to ask and has to do more work. You don't find a generic information model. You find a specific model tailored to answering a particular question. So this is the MBrainz schema, and it shows that you have artists. Artists have albums. Albums have tracks. Artists have countries, and so on and so forth. This is the data set that we're working on. This data set is about 100 million datums. So as of the time we imported it, it was everything that people knew about these things about the music industry. And the result of my sort of reorganization along the principles that we've talked about here is a system that looks like this. And I know that may be a little bit hard to read the words in the back, but walking through from the top, you have a Postgres database, and there's a process called the extractor. The extractor pulls the stuff out of Postgres using Clojure, Java, JDBC, and queries. And the one other thing the extractor does is it goes ahead and joins, and it finds globally unique identities for the things that are being joined to, as opposed to just the Postgres relative numbers, which I don't care about. So that you get a bunch of, as a result on the outside of that, you get a bunch of entity files, which are just Eden data. Then there's a process called the validator that uses spec. That can tool through the Eden data and say, does it look correct per our specs? If that fails, there's a human, right? There's me. I come in there, back in my long hair days, by that icon. I come in there, and I make a fix, and you run that part of the job again. Then there's a transformer. And this is the place where the most interesting stuff happened. The transformer, and the stuff on the top of the screen, it has solid dark lines, which shows that it actually knows about other things that it's talking to. But the transformer is connected to its inputs and outputs only by a channel. So core async also didn't exist when this job was first written, which means that the transformer really doesn't know anything about where data comes from. It really doesn't know anything about where data goes to. It's easy to monkey around with the system and tap channels and multiplex channels and play around with that stuff. And then the transformer uses 2 things. The transformer has a bunch of data tables that are really just pure data, that are, well, this was the name in the old system, and this is the name we want to call it in the new system. We're going to have namespace names and things like that. And then it has a lookup table of a bunch of transducers, right? That case statement that I showed you before. There's a bunch of transducers that it can use to do the job. And then it takes all those Eden files, processes them, and then puts out another set of Eden files, which are raw transaction data ready to go into Datomic. And then the last piece, the loader doesn't know anything about any of the semantics of MusicBrainz. The loader is actually purely generic Datomic code, right? It knows that there's a bunch of stuff lying around that is in the shape of transaction data, and it does 2 things. It batches that data up, so it gets it into a bigger chunk, and then it assigns a batch ID, and it guarantees, as part of its job, that it either knows if it tries a batch that's already in there, it can say, OK, good, I'm fine with that, or it can avoid trying things that it knows are already in there. So it talks to the database. Now, The objective of organizing this way is to localize my stupidity. I'm sure there are a dozen decisions in here that you could second guess, but the boundary of most of those decisions is blocked at wherever those channels appear. Right? So when I've done something dumb, we can make it smarter by just making a change locally. That's the real benefit here. I'm not promising, and this is my real objective. My objective as a software developer is not to be smart. It's to really to limit my stupidity to small local scopes, so that when I need to make a change, it doesn't sort of percolate throughout the system. And to that end, because I've described these transformations as transducers, right? I actually had threading information on here. It showed how parallel the various jobs were, but I've taken it out, not because you might not want to communicate that to somebody if you were handing off the system, but because I want to emphasize how much this design doesn't care. Right? If you said to me, I'd like for you to parallelize some step, I'd be like, okay, that's going to be a 1 or 2 line code change somewhere. If you said to me, you missed a step, you need to break this thing into 2 steps that has an additional thing, then I'm going to take something, split it apart, put 2 more channels between it, and add 2 steps. If you said, you know what, I don't need the durability, I don't need all those files in the middle. Well, how much does the system care about those files in the middle? It doesn't really. And in fact, the old part of the system that I didn't really touch this time around still actually talks directly to files, but if I continued down this road, I would have that talk to channels as well. And at that point, if you said, you know what, this is going too slow, and I see that you have stopped in the middle and made this thing durable, why don't you just take the output of that one and pipe it on to the input of the next one? Right? No problem, right? You just pull that piece out, and then instead of having a channel serialized to Eden, serialized back from Eden on a channel, you just wire those 2 channels together. Or you just make it a single channel, and you compose the transducer that's in that channel. So this also uses channels that have transducers on the channel. So you can say, I'm going to, and you can, again, whenever you have a transducer on the channel, that transducer may be a composition of 4 jobs. So if you decide that one of those jobs needs to be different or add a 5th job, it's a 1-line change on the transducer. That 1-line change doesn't know anything about source data, doesn't know anything about target data. It just knows about the job that it's doing. So I think that this is getting much closer to delivering on the promise of what a good ETL job would look like in Datomic and Clojure. And just to give you some numbers, in the course of doing this job, there's about 100 lines of code that are general purpose ETL helpers. Right, that really have nothing to do with the job at all. They have to do with things like grabbing data from Eden and putting it on a channel. And so that stuff could be in its own library or whatever. There's about 50 lines of generic Datomic ETL helpers. This is like batching and checking to see if the batch has already been submitted and that sort of thing, which don't know anything about the batches. There's about 100 lines of just data lookup tables. So I don't really think of this as code at all. Right? This doesn't contribute to the complexity of the system. This is just data that says, the name in the artist table becomes artist/name in the destination database. There's about 50 lines of specs, and there's about 150 lines that actually do the job. Right? Really, the job here is about 150 lines of code. That's about a half and half split between transducers and wiring. And by wiring, I mean instantiating channels, knowing where the names of files are if you're writing to files and stuff like that. So that's really all sort of glue code. And the interesting part, the transducers, is under 50 lines of code. The other interesting thing that I want to point out here is that the thing that I think is most variable here is the number of lines of code that were specs. That could have been 0. In fact, it used to be 0. Right? You could fly completely naked without specs and not care. That could easily be triple, if not quadruple. Right? We could spec more things. I could spec not only the format of the entities, but I could also spec the transaction data. I could have a second validator. Right? At every step, I could do those things. And what I want to drive home here is the importance of being able to spec exactly as much as you want to make yourself feel confident, and having written those specs, then run them exactly as much as you want to make you feel confident. So for example, having run all the data through the specs once, let's say that this is an import job that has to be run again and again. So rather than being the MusicBrainz import, this is a batch import to a Datomic system that happens once a week. Right? It's an online transaction system, but it also gets a batch of reference data that gets updated occasionally. You might decide at some point that the specs were more about proving to you that you understood the system and less about that you trusted the person that was giving you the data. You could just take that step out. Again, all those things end up being 1 line of code. So in summary, the combination of tools that I have here are enough to help my dumb self feel powerful. Right? The many times that I approached this job before, I felt powerful, but not quite as powerful as I should. And this time, I just felt awesome. Going through this data, I felt that the combination of async and specs and transducers and datomics features, universal schema, and reified transactions, the whole picture of that made me feel like I had total control of this job and that I really could go in and make changes with surgical precision. So I'm pretty excited about it. Of course, it's going to be open source. I'm still putting finishing touches on it, but I'll put up a GitHub repo where you can look at this and download the data and try it for yourself. This also targets Datomic's new client API, which we shipped on Monday. So it's a chance, if you haven't seen the client API, to look at that. Obviously, it would be, again, another example of a few-line code change to make it target the existing Datomic Pure API. That's it. Thank you.